Hello friends. Today I will discuss one of the important molecular rearrangement, dienone-phenol rearrangement. Acid promoted rearrangement of disubstituted cyclohexadienone to a disubstituted phenol is called dienone-phenol rearrangement. That is, acid promoted rearrangement of disubstituted cyclohexadienones to disubstituted phenols, that is referred to as dienone-phenol rearrangement. Here, a dienone is converted into a phenol. The reaction can be represented like this. See, it is a dienone, 1,4 dienone, 1, 2, 3, 4, 1,4 dienone. This 1,4 dienone, in presence of acid, rearranges to form phenol. Here alkyl shift 1 to alkyl shift takes place. In this case 1 to alkyl shift takes place. And by this rearrangement we get phenol. Okay, it is an example of dienone-phenol rearrangement. The mechanism of the reaction can be represented like this. First of all, this dienone reacts with acid. Oxygen capture a proton from the acid, forming protonated dienone. Then 1 to alkyl shift. This alkyl group shifts to the second position through this shifting of electron towards oxygen. Thereby, we will get this carbocation. It is a more stable tertiary carbocation. Finally, a proton is eliminated to form the phenol. Okay, it is the mechanism of dienone-phenol rearrangement. If we treat a 1,3-dienone with an acid, this phenol is obtained. Rearrangement takes place as in the previous case, forming this phenol. You know, the mechanism in the case of 1,3-dienone is like this. First of all, as in the previous case, protonation of this 1,3-dienone takes place to form protonated 1,3-dienone. Then pi electron shifts towards this oxygen, followed by the shifting of pi electron from the cyclohexadiene ring, thereby forming a secondary carbocation. To this secondary carbocation, an alkyl shift, 1, 2 shift. Here, these are alkyl group. One of the alkyl group shift towards this carbon atom, and hence we can say 1, 2 alkyl shift here take place to form this carbocation. It is a tertiary carbocation, you know. It is secondary carbocation, but this is more stable tertiary carbocation. Then a proton is eliminated, thereby forming the final product, the phenol. In this case, the migrating groups are electron donating methyl group and electron withdrawing ester group. We get this product by shifting the electron withdrawing group to the second position. Here 1, 2 shift of electron withdrawing group, not electron donating group, take place to form this phenol. And so we will get this phenol, not this phenol. Usually when there is an electron withdrawing group and an electron donating group in the as the substituent in dienone, only the electron withdrawing group migrates. It is because, you know, these carbocations formed by the migration. If the electron withdrawing group is migrated, this carbocation is formed. You can see this tertiary carbocation is attached with this electron donating group. But in this case, if the electron donating group is shifted, this carbocation is formed. And this positively charged carbon atom is attached with the electron withdrawing group. This carbocation attached with the electron donating group is more stable than this carbocation which is attached with the electron withdrawing group. Thus, only the electron withdrawing group gets shifted, and hence we get this product, not this product. And so we can say when there is an electron withdrawing and electron donating groups as the migrating group in a dienone, only the electron withdrawing group shift to form corresponding phenol in dienone-phenol rearrangement. Okay, if we treat a substituted dienone with an acid in aqueous medium, usually a meta derivative of phenol is obtained. But if we treat substituted dienone like this with acid in non-aqueous medium, usually para substituted derivative of phenol is obtained. For example, this dienone on treating with acid in aqueous medium, the mechanism of reaction proceeds in such a manner to obtain a meta derivative of phenol. Meta derivative of phenol. You can see the mechanism. First of all, protonation of dienone takes place to form protonated dienone. Then by pi electron shift towards this oxygen, we get this carbocation. It is a secondary carbocation. By the 1,2 shift of this alkyl group, we will get a tertiary carbocation which is assumed to be more stable than the secondary carbocation. Then deprotonation, or by the elimination of proton, we get this meta derivative of phenol. It is meta derivative of phenol is obtained if we treat this type of substituted dienone with an acid in aqueous medium. But if we take the same dienone in non-aqueous medium by treating with acid, we will get para substituted phenol. You can see the mechanism like this. Here the pi electron shift takes place like this, thereby first form this carbocation. It is already tertiary carbocation. Then this alkyl shift, not this methyl shift, but this alkyl shift takes place to form a spirine derivative. It is a spirine derivative carbocation which having structure like this spirine. Then ring expansion takes place. Ring expansion takes place with the shifting of this pi electron to this carbon, and ring expansion takes place by the shifting of this bond to this in between these two carbon atom, because it is positively charged tertiary carbon atom. Thereby by this electron shifting, you will get this expanded ring protonated phenol, and as in the previous case, deprotonation in order to have the aromatic ring or for the aromatization, forming the final product. It is para substituted phenol. And so we can say if we take substituted dienone like this in non-aqueous medium and treated with acid, we will get para substituted phenol. But if we take this type of dienone in aqueous medium, for example aqueous HCl, we get this meta substituted derivative of phenol. But if we take non-aqueous medium like sulfuric acid in presence of acetic anhydride, on treating the same dienone with acid, we will get the sulfuric acid, we will get this para substituted phenol. But we take this dienone in non-aqueous medium such as sulfuric acid in acetic anhydride. This is another example of dienone-phenol rearrangement. This dienone on treating with acid followed by treating with acetic anhydride, the acetate of corresponding phenol is obtained. See the product. It is the acetate of the phenol obtained by the dienone-phenol rearrangement of this molecule. See the mechanism of the reaction. As in the previous case, first of all, protonation of this dienone takes place to form protonated dienone. Then shifting of pi electron towards this oxygen takes place. and this leads to the formation of this carbocation, the tertiary carbocation. And to this tertiary carbocation, the alkyl shift takes place from here. Thereby, the ring contraction takes place to form a spiro derivative. This uh, new carbocation is formed by the formation of this spiro derivative. Then ring expansion takes place within the spiro derivative, thereby forming this positively charged cation, and by aromatization forming phenol, and the formed phenol reacts with acetic anhydride forming the final product acetate. You can see the mechanism here. Aromatization takes place by the elimination of a proton, and then the product phenol formed reacts with acetic anhydride forming the final product acetate. This can be represented as this. It is the final product acetate obtained by this reaction. This is another dienone-phenol rearrangement. This dienone reacts with acid. Rearrangement takes place to form this phenol. The mechanism of this reaction can be represented like this. As in the previous case, first of all, the protonation of this dienone takes place to form protonated dienone, then shifting of pi electron towards oxygen, leading to the formation of carbocation. It is a secondary carbocation. By shifting one of the alkyl group to this secondary carbocation, whereby forming a tertiary carbocation, and by the elimination of a proton forming the final product, this phenol. It is the mechanism of the dienone-phenol rearrangement take place in this reaction. See, this is another important example. This dienone, on treating with methyl sulfonic acid, dienone-phenol rearrangement takes place to form this phenol. See the mechanism of the reaction. First of all, as in the previous case, protonation of oxygen atom of the dienone take place to form this protonated dienone. And then by the shift of pi electron towards oxygen, this carbon becomes secondary carbon atom, whereby an alkyl shift, this alkyl group shift to this secondary carbon atom, leading to the formation of a more stable tertiary carbocation. And from this tertiary carbocation, a proton is eliminated to form the final product. Okay, see, this is another important example of dienone-phenol rearrangement. This dienone, on treating with the sulfuric acid, forming the phenol. See the mechanism of this reaction. First of all, as in the previous case, protonation of oxygen atom of the dienone take place to form protonated dienone, then shifting of pi electron towards oxygen atom, thereby forming a secondary carbocation. To this secondary carbocation, this alkyl shift takes place, followed by the ring expansion forming a more stable tertiary carbocation like this, and by the deprotonation, or by eliminating a proton from here, aromatization of the ring takes place to form the final product phenol. Okay, it is the product of this rearrangement, dienone-phenol rearrangement. See this example of dienone-phenol rearrangement. This, on treating with HCl, dienone-phenol rearrangement takes place to form this phenol. See the mechanism of the reaction. As in the previous case, protonation of dienone takes place to form this protonated dienone, the shifting of pi electron towards oxygen, leading to the formation of a secondary carbocation, and then shifting of this alkyl group, 1,2 shift, alkyl shift takes place here to form a more stable carbocation, tertiary carbocation. From this tertiary carbocation, a proton is eliminated for the aromatization. Thereby, this ring becomes more stable, and aromatization takes place by the elimination of a proton to form the final product. It is the phenol obtained by this reaction. Okay. See this dienone-phenol rearrangement. This dienone, on treating with the sulfuric acid, this phenol will be obtained. See the mechanism of this reaction. Sulfuric acid reacts with this dienone. First of all, protonation takes place, forming this protonated dienone. As in the previous case, shifting of pi electron towards oxygen, leading to the formation of a secondary carbocation first. To this secondary carbocation, 1,2-alkyl shift. Here 1,2-alkyl shift takes place, and ring expansion followed by a more stable carbocation is formed. And from this carbocation, a proton is eliminated in order to have the aromatization, and thereby the final product phenol is obtained. It is the mechanism of this dienone-phenol rearrangement. Okay, it is the last example in this video. This dienone, on treating with HCl, forming this phenol. It is the corresponding phenol obtained by the dienone-phenol rearrangement of this steroid with the concentrated HCl. See the mechanism of the reaction. First of all, protonation of this oxygen of the dienone takes place. Thereby protonated dienone is formed. Then shifting of pi electron towards oxygen, leading to the formation of a secondary carbocation. And to this secondary carbocation, methyl shift. This methyl group shift from this position to this position, or 1,2 methyl shift takes place to form more stable carbocation. That is the tertiary carbocation at this position. And for aromatization, deprotonation takes place from this tertiary carbocation, thereby forming the final product phenol. So these are the some of the important examples of dienone-phenol rearrangement and their mechanism. I hereby conclude this video. Thank you for watching. Thank you.